Hello, welcome back to this course on structure, stereochemistry and reactivity of organic molecules and intermediates, a problem solving approach. Today, we will be starting a new concept that is what is called the stereoelectronic effect, which controls the conformation and reactivity of the molecule, and also we will continue to apply the stereoelectronic effect concept onto the cyclization conditions, that means acyclic molecules to cyclic molecules conversion, how the stereoelectronic effect plays an important role, and then we will go to the problem solving approach. Okay. So, first we will discuss the stereoelectronic effect, now which controls the conformation and reactivity of a molecule. Okay. Now, we know that a molecule can suffer broadly two kinds of effects, one is steric effect, another is stereoelectronic effect. Okay. Now, let me so basically the effects that dictates the conformation of a molecule, okay, is broadly a steric and stereoelectronic. Okay. Steric, we know that steric basically is the when two groups become very close to each other, then there is a kind of repulsive force that that occurs, and that tries to pull the two groups away from each other. So, this is what is the steric effect, and we say that the molecule is suffering from some steric strain. Remember, steric effect, if you think the atoms as rigid balls, then steric effect is basically kind of a mechanical effect, but actually it is not. It is actually surrounded by electron clouds. So, whenever we talk about steric effects, basically it is the repulsion between the electron clouds when one enters the domain of the other. So, that is also a kind of electronic effect, but it is actually segregated from the stereoelectronic effect. When we talk about stereoelectronic effect, we are not considering the steric effect. Here it is mainly the electronic effect which is possible due to the overlap of certain orbitals with electrons. Okay. So, there is this distinction. Now, steric effect controlling the conformation of a molecule we are extremely aware of. Like if I ask you that what is the preferred conformation of 1,3-dimethyl cyclohexane, okay, 1,3-dimethyl cyclohexane cis, then you know that this is possible, one conformation which is possible, but the other conformation is more stable. So, here the two methyl groups become equatorial. Okay. And because of steric effect between these two methyls as well as the steric effect with the axial hydrogen, the molecule adopts the preferred conformation which is diequatorial. So, this is a classic example of how steric effect operates and how it dictates the conformation of a molecule. Now, stereoelectronic effect is very similar, that instead of these groups, if you have electron clouds here, okay, in the form of orbitals, then if they are pointing towards each other, then what will happen? They will repel each other, and that also creates some kind of an effect, and that is what is called stereoelectronic effect. That, so, it means that stereo means we know it is 3D space and electronic. So, combined, that means the spatial orientation of the orbitals can create stabilization or destabilization. It both possible, as the case may be, stabilization or destabilization that can happen, and that effect is what is called stereoelectronic effect. So, definition will be basically the stereoelectronic effect is the effect that is operated between electronic that operating between the orbitals or the bonding orbitals it could be, or it could be bonding and non-bonding orbitals, and the molecule try to adopt a conformation where the electronic repulsion becomes minimum and the molecule takes up a stable conformation. Like in the case of steric effect, the molecule tries to adopt a conformation where the steric effect is minimum and the molecule gains stability by doing that. Similarly, if there is electron-electron repulsion, the molecule will orient or change into another conformation in such a way that those type of repulsion is minimized. That means, the molecule does it to gain stability. Okay. The other possibility, this is what is repulsive, when there are repulsive that electron-electron interaction. Sometimes what might happen, that the molecule adopts a conformation where there is a possibility of extra overlap between some orbitals which was not possible earlier if it takes another conformation. Okay. So, that is a stabilizing effect. That means, the molecule adopts a particular conformation where the orbitals are positioned geometrically in such a way that there may be some meaningful overlap between the orbitals and the molecule gains stability. That is one aspect. Other aspect is that if there is too much electronic repulsion, then the molecule adopts some conformation where this repulsion, that means the orbitals go away from each other. Okay. All types of possibilities are there. Okay. So, let us give an example of a stereoelectronic effect controlling the conformation of a molecule. See, sorry. Let me try to draw it. Two chair forms, there is an oxygen here, and if there are two sulfur at these two centers. Okay. Now, the sulfur has lone pairs like this. Now, this is a molecule, it is a bicyclic molecule where it can adopt containing two sulfur and one oxygen, and the sulfurs are pointing downwards. Okay. Both are basically there are two chair forms in this, there are two chair forms. So, apparently they should be quite stable, but what happens here, that because the sulfur groups are pointing downwards and their orbitals, that means the non-bonding orbitals which are containing electron pair, lone pair of electrons, they repel each other. So, there is electronic repulsion if the molecule assumes this type of conformation. Okay. So, because of this stereoelectronic effect, the molecule now changes its conformation and takes up a conformation where this is minimized. It is the same molecule, but the two sulfurs are pointing oppositely to avoid that electron repulsion. Okay. So, now, so this is an example, a classic example how stereoelectronic effects dictate the conformation of a molecule. Okay. Now, let us try to see what is the origin of this stereoelectronic effect. Now, remember that in a cyclohexane system, what happens that if you have a cyclohexane system and if it is conformationally locked, the way to do it is that to put a tertiary butyl. If it is conformationally locked, and if you want to or not conformationally locked, suppose it is a flexible system and you put a group, an alkyl group. Okay. So, it is a monosubstituted cyclohexane, and if you try to determine its preferred conformation, we know that the preferred conformation is the one where the R is equatorial. Okay. The R is in the equatorial form, okay. And we know the reason for that. When you have, suppose I have an oxygen here and still I put a R group where R is alkyl. Remember, R is alkyl group. If R is alkyl, then also the preferred conformation is the one where the R is assuming an equatorial conformation. Okay. So, this is the way things were. Okay. Then suddenly what happened, that if you change this character of R, if you change the character of R and put a polar group, like if you have before that let me see that even if you have wedge here and wedge there, and suppose it is in the form of glucose molecule, so this is beta glucose and this is alpha glucose. Still the axial one is not the preferred one, the equatorial one, that means the beta glucose is the preferred one, and the ratio is about approximately 33 and 67%. And you know the classic case of muter rotation, that tells you that what is the equilibrium value, at the equilibrium what is their percentage composition. Okay. So, up to this point our original notion that a substituent, when it is incorporated in a cyclohexane system, then it prefers to assume the axial orientation. However, this concept got severely challenged when people found that if you have, instead of wedge, if you have OMe, a methoxy, then there is complete reversal, it is the other way around. That means, this is almost 2 and that is almost 1. Okay. That is 1 and that is 2. So, the ratio got reversed. The same is true if you have OCOCH3, that means acetate. Okay. I am not writing the other groups like this. If you have acetate, then also the that axial one was preferred, and the preference actually got increased. That means, the percentage of the axial one is even higher than what was for methoxy. Okay. And then with Cl here, you have a 90 to 10% of the 90% of the axial chloro compound versus 10% of the equatorial chloro compound. So, something happened when you have a polar group like Cl, methoxy or acetate attached to this carbon. By the way, this carbon is what is called what is known as the anomeric carbon. Okay. The anomeric carbon is basically the original aldehyde carbon, which is converted into an hemiacetal by intramolecular cyclization, and then that hemiacetal, from that hemiacetal the carbon came to know as anomeric carbon, because it is as the alcohol, as it forms the hemiacetal, you create another stereogenic center, and that is the genesis of alpha and beta anomer of glucose. Okay. So, this is called the anomeric carbon. So, if you have a substituent at the anomeric carbon and if it is polar, then what happens? The polar group tends to occupy an axial orientation. Okay. This is nothing but a stereoelectronic. The reason is stereoelectronic effect. The reason is basically a stereoelectronic in origin. However, this has got a special name, and that is what is called the anomeric effect. Okay. The anomeric effect. What is anomeric effect? The anomeric effect is basically the preference of a polar group at the anomeric carbon to adopt an axial orientation in an axial orientation in a sugar. Obviously, anomeric carbon is there. That is what is called the anomeric effect. Okay. So, basically this is the starting point of people then tried to look at the genesis of this anomeric effect, and when it was explained, when it was known that why there is this particular preference, then they started looking at the reactivity of similar systems, and they could come out with explanations that how to explain the reactivity of very similar systems, okay, based on this stereoelectronic come the anomeric effect. Again I repeat, anomeric effect is a part of a stereoelectronic effect. Okay. Now, let us there are two things now. Basically, one is we realize that there is a preference for the axial orientation of a polar group at the anomeric carbon. But the question is there any quantitative measure of this anomeric effect in case of an ether system? Is there any quantitative measure? So, that is one aspect. Yes, there is some quantitative measure that how much is the anomeric effect, what is the kilocalorie per mole. Like we know that a gauche butane contributes around 0.85 to 0.9 kilocalorie per mole. So, that is the evaluated parameter. Okay. So, similarly, that is one aspect, and the other aspect is that explanation of the anomeric effect. Okay. Now, the explanation of the anomeric effect is there could be two schools of thought. Okay. One school of thought is basically concentrating on the destabilizing effect on the equatorial isomer. See, you can look into this problem into two ways, that either there must be something which is destabilizing the equatorial isomer, that means when the polar group is in the equatorial position, or you can look it into another way, that there must be some stabilizing interaction which is absent in the equatorial form. So, one is a stabilizing effect which stabilizes the axial isomer, another is the destabilizing effect which destabilizes the beta isomer. Okay. So, you can try to explain in both ways. So, these are the two schools of thought. Now, let us see the first one, that what makes the beta unstable, from what interactions it is, what extra interactions or strain it is suffering from. Okay. So, let us draw the beta isomer. Remember, this is a polar group. Okay. So, this atom is much more electronegative than the carbon which it is attached, that means the anomeric carbon. Okay. So, when you have this molecule and you know that put the oxygen lone pairs. So, one is axial lone pair, another is equatorial lone pair. So, basically now because of the inductive effect, this will assume also delta negative character. And if you see, there is the dihedral angle between this lone pair and this x is 60. So, also the dihedral angle between this lone pair and x is 60. That means, if you draw a Newman projection along this is your C1 carbon. So, how does it look? So, this is 1. So, your hydrogen is at the bottom, then you have x, and then you have this is your 6, this is your number 2 carbon. So, this is your number 2 carbon, and then you have the behind is oxygen, and the oxygen lone pair, the axial lone pair is like this, and the equatorial lone pair is like this. Okay. So, this is the situation, and this is the other. This is basically the 6th, not 6, this is the 5th carbon, 1, 2, 3, 4, 5. So, this is the carbon number 5. So, that is the Newman projection of this. So, if you draw the Newman projection, now you see that this is basically a delta negative, which is now sandwiched between two lone pairs. Okay. So, that creates lot of electronic repulsion. Okay. So, lot of electronic repulsion because they are actually in the gauche form, okay, because the diagonal angle is 60 degree. The Cx and the direction of the lone pair, they are making an angle of 60 degree. Okay. So, that basically destabilizes this system. Now, the question is it present in the axial isomer or is it present, but maybe in a less, to a less extent, but let us try to draw that. So, draw the axial isomer. This is hydrogen, this is the lone pair, this is the lone pair, sorry. So, if you now try to draw the same thing, same Newman projection, so you will have now the oxygen, that lone pair is there, axial lone pair, this is the equatorial lone pair, okay. And now this is your C5 carbon, and you have on the top number 1. So, X is here, here it is hydrogen, and on the other side it is 2. Okay. So, these are the two Newman projection for this. Now, in this case you see there is only one lone pair X gauche interaction. So, 1 versus 2. So, that means because of these lone pair and the polar group interaction. So, this is preferred. Remember, preferred that means this interaction energy is quite high, because when X is axial, then you have an axial diaxial 1,3 diaxial interaction. So, that must be overcome by this electronic interaction. So, even if you are inducing some repulsion here, but that is not sufficient. This is much more. So, what I am saying that if it is x kilocalorie per mole, that is x kilocalorie per mole, and this is x, and the extra thing that it has is this one, suppose that is y, but we can say that x plus y is the stabilization is less than 2x. Okay. So, that is what is basically. So, even if we induce some diaxial interaction, but you are actually, that is much more being compensated by the reduction of one of the lone pair and X gauche interaction, which is an electronic repulsion. Okay. So, this is one idea, that why the group X occupies the axial position, preferentially occupies the axial position. Another school of thought is basically based on the no bond type of resonance. No bond resonance, you know what is a no bond resonance, that is also known as hyperconjugation. Okay. So, another school of thought explains it on the basis of resonance. See, this lone pair is exactly anti-periplanar to the CX bond. Okay. If that be the case, then what happens, this lone pair can come onto this side and then break the CX bond, and in the process it can generate a structure which will look like this. It is a resonance structure O plus X minus. Okay. This is happening because of the geometric relation between this CX orbital and this lone pair, because they are positioned in space in such a way that this type of displacement can take place. Okay. This is very similar to your any addition or elimination, beta elimination or 1-2 addition. You know that the groups are adding in an anti-periplanar sense, or when they eliminate in an anti-periplanar, they have to be in an anti-periplanar position. That is also this anti-periplanarity for a beta elimination is also what is called the stereoelectronic requirement for the reaction. Okay. So, you see this stereoelectronic term is used in many places. It is basically in case of conformation. If I am talking about the conformation, and stereoelectronic effect, then the conformation, the preferred conformation becomes such that the repulsion between the orbitals that are positioned in the space becomes minima. That means, the orbital takes up a position in the 3-dimensional space in order to minimize the repulsion between the electrons. Okay. That is when you are talking about the conformation. When you are talking about the reactivity of a molecule, then what is the stereoelectronic effect, or what is the stereoelectronic requirement that we say? The stereoelectronic requirement is that the molecule must adopt a transition state while it is reacting with the reagent, with the attacking reagent. It actually should take up a geometry where the orbital overlap is maximum. Orbital overlap is maximum, means when a reagent approaches a molecule, there must be an interaction between the two, and this interaction is what? Interaction, overlap of the orbitals, interacting orbitals. So, the attacking reagent must approach from a side which assures maximum overlap that is possible. Similarly, when the group leaves and a new bond is formed, so the bond formation also has to be done with maximum overlap principle. Okay. So, that means the orbitals should be positioned in the space in such a way, so that it gives the maximum overlap possible, and that is the stereoelectronic requirement of an E2 elimination. The stereoelectronic requirement of an SN2 reaction is that the nucleophile approaches opposite to the side of the leaving group. Not only that, it approaches collinear, its line of attack is collinear with the carbon leaving bond. Why is that? Because if it approaches only in a collinear fashion and opposite to the leaving group, then there is maximum possibility of overlap with the back anti-bonding orbital that is there for the Cl bond. Okay. Cl sigma star has a lobe at the back side. So, when the nucleophile attacks from the back side and exactly aligned with the Cl bond, then only the maximum overlap takes place, and that is what is called the stereoelectronic requirement for an SN2 reaction. Okay. So, in terms of conformation, the electronic repulsion has to be minimized, or there must be some possibility of new type of interaction which stabilizes the isomer. Okay. Like in anomeric effect, what I am saying that when X was equatorial, there is no chance of this type of resonance possible because of the positioning of the CX and the lone pair. They are not antiperiplanar in case of the equatorial isomer. Okay. So, there is no antiperiplanarity here. So, such type of resonance is not possible. So, now you can say that this molecule is a resonance hybrid of this, and that gives the extra stability to the molecule. Okay. Now, if that be the case, if it is a resonance hybrid of the two, how can you prove this experimentally? The way to prove is that this CO bond should be now shortened due to this resonance, which is indeed have been found to be true, that this CO bond is shortened in this case of anomeric systems. When X is axial, when X is equatorial, you do not see the lengthening of the CO bond. Okay. So, that is a good proof that this type of resonance is happening. However, this type of no bond resonance, this is a valence bond approach. This type of resonance structures some people may not like, especially when you use the molecular orbital picture. So, there must be a molecular orbital picture of this type of resonance, and that is we can discuss that now. So, now we have two theories. One is that that lone pair and the CX gauche interaction that is more in the case of equilateral isomer, and the second one is this type of resonance, no bond resonance, a hyperconjugative resonance, which is possible only for the axial isomer. Okay. Now, the third one is a molecular orbital approach. What it says that when you have this X, CX, sigma bond, so there is an antibonding orbital for the CX, and that has got a lobe on the opposite side, okay, and that has got a lobe on this side, which is vacant. Okay. And these two, this lone pair and this vacant, this is the this is the sigma star of the CX bond. Okay. So, that orbital is vacant, but this is lying exactly parallel to the lone pair. So, now there is lateral overlap which is possible. So, if there is lateral overlap possible, that means these that will be basically this is empty, that is the sigma star, and that is the lone pair, that is the non-bonding lone pair. So, that gives a stabilization, overall stabilization of the system. Okay. So, basically the third one, which is basically the modern approach, this says that the anomeric effect is due to the fact that there is a lower overlap, there is an overlap between the axial lone pair on the oxygen and the antibonding sigma antibonding orbital of the CX bond, because they are in 3D space, they are perfectly positioned to interact with each other. It is like a pi bond, that when you have a pi bond, the p orbitals are lying parallel to each other, and then you have the sidewise overlap. So, that same thing can happen here, and that gives the extra stability for the axial isomer, and that is why you see the anomeric effect dictating the x to be at the axial position. Okay. So, that is what is the anomeric effect. Now, another interesting point I should also mention here, that is this anomeric effect now can be very general. It does not have to be in a sugar molecule. It can be of any system where you have this type of like see what is the anomeric system, oxygen, then a carbon, then an oxygen, and here you have a lone pair. Okay. So, this type of system is also can be present in other molecules, like if you have say O, then Me, okay, and then a CH2, and then O, and then Me. So, now you have this lone pair here, lone pair there, lone pair here, lone pair there. Now, usually this type of linear molecules take a zigzag orientation, conformation. Okay. However, this molecule takes up an orientation which looks like this, contrary to what we usually think. Okay. So, now there will be a lone pair here, there will be another lone pair somewhere there, there will be a lone pair here, there will be a lone pair there. Okay. Now, this is again because of the anomeric Tyche effect, the effect that we have seen in the sugar moiety. Okay. Now, when you have these, remember in the anomeric effect, the lone pair which is participating in the anomeric effect is attached to the heteroatom. It is not necessarily always oxygen, it could be nitrogen also, and then you have a bond and then another one which is attached to another heteroatom. So, basically now you can say that anomeric effect can take place in any system which will have this type of attachment. okay, this type of attachment. So, X carbon X, and this X should have this here O had a R group, okay, because this is either methoxy or acetate, those type. So, you can say that this has got a R group. Okay. So, this type of system will also show anomeric effect. Now, the point I was trying to make out is that this lone pair on the X is basically anti to the bond, to the beta bond, okay, to the beta bond which is attached to another heteroatom. Okay. That means, I can say that if a molecule looks like this, adopts this type of conformation versus suppose these two. Okay. Now, this is exactly the system which can generate anomeric effect, okay, because this is anti to this beta bond. Okay. However, here this is not anti to this bond. Okay. So, if a system adopts this type of conformation, there is one anomeric effect. If a system adopts this type of conformation, there is no anomeric effect. Okay. So, this concept is very important, because sometimes you may be asked that how many a molecule can have multiple anomeric effects present, and the way to find out is basically you have to check the lone pair and then see whether there is a beta bond which is attached to another heteroatom and that is anti to it, then only you can have an anomeric effect. Like here, these two systems, there is no anomeric effect in this conformation. But here now you have, this is the lone pair and this is the bond I am talking about, which is anti to each other. Okay. So, there is one anomeric effect here, and there is another anomeric effect which is between this and between this. So, there are two anomeric effects. Okay. So, this concept will we can do one problem. I think that will clarify the number of anomeric effects that are possible in a molecule or that are present in a molecule. Let me try to find out the system. Okay. There is one molecule which is a fusion of a pyridine and something which is called an oxygen. You know that heterocyclic ring, these are of course tetrahydro, that parhydropyridine, means tetrahydropyridine and this is also the fully hydrogenated form. This is what is called oxygen, this system, and this is what is called pyridine, means loosely speaking these are actually reduced pyridine and reduced oxygen. Okay. So, we have a fused system between the two. Okay. Now, it can exist in the trans form or it can exist in the cis form also. Okay. Let me try to draw the cis form in, and the cis form is, so this is the cis form. Okay. So, now the question is which one will be more stable, which one will be more stable. The other way, I think the other way I can draw it is rather than changing that, let us change this part. Okay. So, this is the nitrogen. Okay. Let us, this is also perfectly okay, we leave it here that, but we draw another conformation which is same as that. This is the cis, and because the lone pair is this and this is the hydrogen, here the lone pair and the hydrogen are trans. So, this is the trans system and this is the cis system. Okay. Now, let us try to find out whether there is any anomeric effect present in these systems, or there is and if it is present, how many are there. Now, one more thing that comes into mind, that we started with the anomeric effect with a substituent at the anomeric carbon. Here there is no substituent as such, no? But you can think that one heterocycle can provide substituents to the other heterocycle. So, that creates the genesis of the anomeric effect in these systems. Okay. Now, in order to find out the anomeric effect, correctly draw the lone pair of electrons and the heteroatoms. Okay. So, this is the first one, the trans, and the second one is this, and there is a lone pair here and there is a lone pair there. Okay. Now, try to find out what I said, that you have to find out that whether against the lone pair there is a beta bond which is anti, and that beta bond has to be attached to a heteroatom. Okay. It is not that the beta bond will attach to a, suppose if you have this and then there is a carbon and there is a carbon, then there is no anomeric effect. Okay. It is only possible if there is a heteroatom here, then only its sigma star can meaningfully interact with this. Okay. It is not carbon, it is another heteroatom. Okay. So, let us see, this is the lone pair on the nitrogen, and I could see that the lone pair, then the beta bond which we are talking about, that means the lone pair, then a carbon, then a atom, and then the next bond. So, the lone pair, this is the bond, and then there is basically no atom which is highly electronegative. So, basically this lone pair does not provide any anomeric effect. On the other hand, this lone pair, the oxygen lone pair which is equatorial, so if you look at this actually satisfies the condition of anomeric effect. So, that gives one anomeric effect. This oxygen lone pair which is axial, again that is not giving any anomeric effect, because nothing is, what is anti to it is a hydrogen. So, that cannot give a anomeric effect. So, there is one anomeric effect present in this, and in the equatorial one, this lone pair and then this bond, and this is the one and a heteroatom. Okay. It is a perfect positioning to give an anomeric effect. So, this is one anomeric effect and this is another one, okay, because the lone pair, then oxygen, then carbon, then nitrogen. So, that means this molecule is suffering, is actually not suffering, is having a stabilizing interaction, because anomeric effect is a stabilizing interaction. It is having two anomeric effect and this is one anomeric effect. Okay. And you can actually calculate the energy difference between these two. Okay. One anomeric effect, I have not talked about how the anomeric effect has been evaluated, maybe in the next lecture I will do that. The anomeric effect can be evaluated, and just take it from me, the anomeric effect has been estimated to be about 1.4 kilocalorie per mole. One anomeric effect is equal to 1.4 kilocalorie per mole. Okay. So, if I ask you that what is the energy difference between the two, first of all see the destabilizing forces, because this is trans ring junction, this does not have any gauche type systems. Okay. We know trans decalene does not induce any extra gauche butane unit. Similarly, there is no extra gauche unit here. Okay. So, it has got a stabilizing interaction of one anomeric effect. Okay. So, the overall energy, suppose this whole skeleton, because it is called carbon, 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 nitrogen bonds. So, if the whole skeleton has an energy of x, then it will have x minus 1.4. Okay. So, that will be the energy of the system, of the trans. On the other hand, the cis, now it is made up of the same molecular formula. So, it will have x, okay. But now, okay, it has got two anomeric effects. So, minus 2.8 but then it has got some plus because it is cis ring junction. First of all, it has got two Gauss butane type interactions. One is this, another is this. Okay. So, two Gauss butane interactions, that gives about, if it is 0.9, so that gives about 1.8, and it has got again another one which is also Gauss, not butane. Now, it is got a, it is like a carbon. If you think this is a, it's a nitrogen, but if it is all carbon framework, that will be called a propyl alcohol. Okay. So, this is nothing but called a Gauss propyl alcohol system, and that gives some additional energy. I think that is about 0.4. So, that is about 0.4. So, now you can, so this is the energy of the cis system, this is the energy of the trans system. So, you can easily make the difference between the two, and you can predict that at equilibrium mixture what will be the ratio of the cis and the trans. Okay. So, I think that is we have given some concept, some clarification, and on stereoelectronic effects. We first introduced stereoelectronic effect, then we started talking about that the genesis. It all started with the anomeric effect, namely in the sugar chemistry, and then what is the reason for having this anomeric effect. We have seen there are various explanations that can be provided to explain the anomeric effect, and then how to calculate the number of anomeric effects that are present in a system. Okay. Thank you very much.